So let's look more closely at what possibilities we've got with our dissolution of sodium chloride. So this graph represents the concentration of silver ions and chloride ions in a mixture of silver ions and chloride ions. The notation here is exponential, so it's the way that Excel represents scientific notation. 3e minus 4 like this means 3 times 10 to the minus 4. We're in moles per litre because it's a concentration. So all of these numbers you just read off as exponentials. 2e minus 4 would be 2 times 10 to the minus 4. 5e minus 6 would be 5 times 10 to the minus 6. Okay. Our x-axis is chloride concentration. Our y-axis is silver ion concentration. And the blue line with the dots on it here represents combinations of concentrations that when you substitute them into the equilibrium expression, they give you exactly KSP. So for instance, this dot here, I've rather stupidly made the scales on the x and y axis different. There's no reason for them to be different. This dot here represents the situation where you have equal concentrations of silver and chloride. That is, where they are both 1.3 times 10 to the minus 5 molar. When you multiply 1.3 times 10 to the minus 5 by itself, you get 1.7 times 10 to the minus 10, which is our KSP. Similarly, if you look at this point here, the chloride concentration is 5 times 10 to the minus 6. It's a bit hard to read on the scale, but the silver concentration is 3.4 times 10 to the minus 5. If you multiply those two values together, you also get 1.7 times 10 to the minus 10. So every point on this dotted blue line is a possible combination that could be at equilibrium because the product of the concentrations is the KSP. All right, now let's have a look at another possibility. Say we've got a system that is, let me just change colours. So we've got a system that's over here. Okay, let's call this point A. So our concentration of chloride is 1 times 10 to the minus 5. And our concentration of silver is 1.5 times 10 to the minus 4. Okay, now if we evaluate Q, so we stick those concentrations into the equilibrium expression. So it's silver times chloride, 1.5 times 10 to the minus 4 times 1 times 10 to the minus 5. That gives us a value of 1.5 times 10 to the minus 9. Now you can see that this value here, 1.5 times 10 to the minus 9, is greater than KSP. So we have a situation where Q is greater than KSP. That means we have too much products. Our concentration of products is too high to be at equilibrium. So all of this area here in the graph is a situation where Q is greater than KSP. That means there's too many products, too many dissolved ions. And how can the reaction get rid of those excess dissolved ions? Well, it shifts to the left. It uses up some of the dissolved ions to produce precipitate. So if for a reaction like this, where it's a dissolution reaction, if Q is greater than KSP, the way the system regains equilibrium is for the excess products, the excess dissolved ions, to precipitate out as solid. At some point, the concentration of silver and chloride will be reduced sufficiently that you'll get back to being somewhere on the dotted blue line, and then you'll have equilibrium. All right, let's look at another possibility. Another possibility would be to have, let's take a situation about here, say. Here is B. And at B, let's say we've got a concentration of 2 times 10 to the minus 6 moles per litre of chloride. And 5 times 10 to the minus 5 moles per litre of silver. We evaluate Q by sticking those into the equilibrium expression, and we get a value of 1 times 10 to the minus 10. And you can see this is slightly lower than the KSP of 1.7 times 10 to the minus 10. So in this case, our Q is less than KSP. This means that we don't have enough products. Our concentration of products is too low. So the way that the system regains equilibrium is to dissolve some of the solid to produce more dissolved ions, to produce more products.